sixth graders, this lesson is on theoretical and experimental probabilities. So make sure you either have the notes packet that you got in class to use to take notes on, or upload that notes template onto Notability, print it off, or just do your notes directly in your notebook as you watch this video. Our learning target is being able to find and compare theoretical and experimental probabilities. So we have theoretical probability and experimental probability. So what is the difference? Theoretical probability, which is a word that you definitely want to have written down in your notes or maybe circled or highlighted on the template, is the probability of what should happen. And then the experimental probability is what actually happens. So this deals with an experiment or a simple event where it occurs more than once, and we're trying to figure out the theoretical and experimental probability of the experiment. If a coin is flipped 10 times, theoretically, how many times should it land on heads? Well, we know that the probability of getting heads, if we flip a coin, is 1/2, because there's two outcomes, either heads or tails. One of the outcomes is heads, so the probability of getting heads is 1/2, and that's just if we have a simple event. We flip it one time, and we have a 50% chance of getting heads. So theoretically, that means that 1/2 of the time we should get heads. So if we flip it 10 times, 1/2 of 10 equals 5. So if we flipped a coin 10 times, theoretically, we should get heads 5 times and tails 5 times. Obviously, we know that that's probably not going to happen, but that's just in theory. If the coin landed on heads 7 times, what is the experimental probability of the coin landing on heads? So we flipped it 10 times, 7 of the times it was heads, so the experimental probability of heads was 7 out of 10, because it landed on it 7 times and they flipped it 10 times. Then we write it in simplest form, which it's already in simplest form. So 70% of the time, or 70% of the flips, it landed on heads. Okay, let's look at a couple more examples. A dice is rolled 24 times. What is the theoretical probability of rolling a 5? Well, if we roll a dice one time, we know that the probability of rolling a 5 one time would be 1/6, because there's 1 5 and there's 6 outcomes. So theoretically, 1/6 of the time, however many times we roll it, 1/6 of the time we should get. Remember, theoretical is what we should get. So if I roll the dice 6 times, okay, 6 times, theoretically, I should get 1 one time, 2 one time, 3 one time, 4 one time, 5 one time, and 6 one time. So if we roll it 24 times, then 1/6 of 24 is theoretically how many times we should get a 5. So 1/6 of 24 is 1/6 times 24. And I'm going to put a 1 under here, because remember, when we multiply by fractions, we want a numerator and a denominator. So it'd be 24/6 divided by 4. So theoretically, we should get a 5 4 times, because 1/6 of 24 is 4. If a 5 is rolled 8 times, what is the experimental probability? So experimental is after this experiment and what happened. So theoretically is kind of before and what should happen. Experimental is after the experiment and what actually happened. So if 5 is rolled 8 times, what is the experimental probability of rolling a 5? So back to that being it rolled 24 times, it was rolled 8 times. So the probability of rolling a 5 in this experiment only was 8/24, and we simplify that. We can divide them both by 8, so we get 1/3. So 1/3 of the time we got a 5. And then we can see that we rolled it more. We got a 5 more than we theoretically should have. In the above experiment, what is the experimental probability of not rolling a 5? So if I rolled a 5 8 times and I rolled it 24 times, 24 minus 8 is 16. So the probability of not rolling a 5 would be 16/24. And then we simplify that. I can divide them both by 8, so I get 2/3. So 2/3 of the time was not a 5. I also can see that 1/3 plus 2/3 should equal 1. So remember complement. So probability of 5 and then probability of not 5. So I could have known right away that if probability of 5 is 1/3, that not 5 would have been 2/3 because these together equal 1. If I spun this spinner 40 times, what is the theoretical probability of landing on a 2? So if you want to pause the video and do these 2 questions in your notebook and then come back and check, that'd be awesome. So if I spun it 40 times, what is the theoretical probability of landing on a 2? So I can see that there's 4 equal spots on the spinner, which means that landing on a 2 is 1/4. So, oops. Let me write it like this. Probability of landing on a 2 is 1/4. So then we know that 1/4 of the time should be landed on a 2. So 1/4 of 40 is the same as 1/4 times 40. 40/4, which 40 divided by 4 is 10. So theoretically, it should land on it 10 times because that makes sense. It would be 10, 10, 10, 10. So theoretically, it should land on it all the same amount of times. If I landed on a 2 16 times, what is the experimental probability of landing on a 2? So probability of a 2 experimentally would be 16. We rolled it 40 times. So then we can simplify it, and I can divide everything by 8. So 16 divided by 8 is 2. 40 divided by 8 is 5. So 2/5 of the time it landed on a 2. The graph shows the results of an experiment in which a spinner with 3 equal sections is spun 60 times. Find the experimental probability of spinning red for this experiment. So we see that red was spun 24 times out of 60. So the experimental probability of spinning red, so notice we always write it with our P, and then in parentheses is what we, like the favorable outcome. Remember that word of what we're wanting to get. So probability of red in our experiment was 24/60 because we spun red 24 times out of 60 total spins. I can divide both my numerator and my denominator by 12. 24 divided by 12 is 2. 60 divided by 12 is 5. So we have 2/5. Compare the experimental probability you found to the theoretical probability. So if it has 3 equal sections, then each probability of each color would be 1/3. So the theoretical probability of spinning red is 1/3. The experimental probability of red, we just found out based on this experiment, is 2/5. If we do the experiment again, obviously, as you know, all of our data would change because we would spin different amounts of different colors. But for this experiment, we can see that we have 1/3 and 2/5. And the easiest way to compare fractions is to get it into a common denominator. So this is good practice from way back when. I know that 3 and 5 can both go into 15, so I'm going to multiply both of these by 5 to get 15 on the bottom. I'm going to multiply both of these by 3 to get 15 on the bottom, so I have 5/15, 6/15. So I can see that my experimental probability is higher than my theoretical probability. So I got red just a little bit more than I should have, or theoretically should have, based on our probability. We also know that 1/3 of 60 equals 20. And so right away then I know that 24 is greater than 20. So my experimental probability is greater than the theoretical. So a couple different ways that you can figure that out. All right, let's look at this example where we can predict what to expect. So a video streaming analyst examines last year's video genre selections of customers. Last year's selections are shown in the table. What is the probability that a person streamed a comedy genre? So this would be, so we would do probability of comedy, and then we look right here. So there's 580 people that streamed comedy, and we would add them all up, and I get 2,000. So 580 out of 2,000 people streamed comedy. So then it says, suppose the analyst expects 5,000 customers this year. How many drama selections should be expected? So based on this experimental probability on these 2,000 people, based on this, what can they expect? So businesses really truly use things like this so that they know what to expect, and it won't be exactly right on, but at least they can have an idea. So then I can do 580 over 2,000, and we can find an equivalent fraction to 5,000 as my denominator. So I know 2,000 times 2.5 is 5,000, so I can do the same thing. 580 times 2.5. And I did make calculations before. You can definitely use a calculator on something like this, but 580 times 2.5 is 1,350. So we know that he can expect about 1,350 customers to stream comedy based on this experimental probability that already occurred. So to recap, this is something you for surely want in your notes highlighted or highlighted in your notes packet. So theoretical probability is what should happen. Experimental probability is what actually happens. So theoretically, if I flip a coin 100 times, I should get heads 50 times and tails 50 times. Experimentally, if I flip it 100 times, I get heads 60 times and tails 40 times. Then my experimental probability is different than my theoretical probability. The higher number of experiments, the closer that the theoretical and experimental will most likely be. So if I flip a coin 5,000 times, then I will get closer to my theoretical probability, and it will be closer and closer to 1/2 heads and 1/2 tails. Not exactly, obviously, but closer and closer than just, say, only flipping it 10 times. And then lastly, here are your you do questions. So do these at the bottom of your notes or right on the notes template. We have two parts of the first question, 2 parts of the second question. Complete those, and then make sure that you have all of these notes with you at your next math class, whether it's in person or on Zoom. Have a great day, everyone.